first thing that we're going to do is, in our notes, take out whiteout or take out just your pen and cross out that word test, because you've learned that the second derivative shows you concavity. When the second derivative is positive, your original graph was concave up, and when your second derivative was negative, your original graph was concave down, and that's an important application of the second derivative. Today, we're going to look at the second derivative test, and the second derivative test is a test for maximums and minimums. So when we talk about the second derivative test, we're not going to be talking about concavity, whether something is concave up or concave down. We're going to be talking about whether the original function had a maximum or a minimum. Now, the first derivative test, do you remember finding where the first derivative was equal to 0? Say it was at 0 at -1 and 3. And then you found if your first derivative was positive, your function was increasing. If your first derivative was negative, your function was decreasing. And then if it got positive again, it was increasing. And from the first derivative test, what can you tell me about -1? What's going to happen on our original graph at -1? It's going to be a maximum, right? And what's going to happen at 3 on our original graph? We're going to have a minimum. That was our first derivative test. What our second derivative test says, if you don't want to look at the first derivative test, which almost always you'll do because it's easy. So most people forget the second derivative test because they can already find maximums and minimums from the first derivative test. But what the second derivative test says, if you find these same points at -1 and 3 and decide not to do that graph where you show where it's increasing and decreasing, but then later you show that, hey, my second derivative is bigger than 0. Now, second derivative being bigger than 0 means that it's concave up. So if it's concave up and you have the first derivative being 0, does that make sense that that would have to be a minimum? And if you're looking at the second derivative and it happens to be negative, and your first derivative says that the tangent's equal to 0, does it make sense that that has to be a maximum? So now we've got to change some words here because we have minimum in both of these. So I get to get our whiteout again. Is it corrected on yours? No. So if we have something concave up and our first derivative is equal to 0 at that point, then we know that it's a minimum. If we have something that's concave down and our first derivative is equal to 0 at that point, then we're going to have a maximum. So that's if you didn't do this first derivative test, you could still find out if something's a maximum or a minimum with the second derivative test. But because the first derivative test is so easy, whenever you're going to be graphing things, you're probably going to do that anyways. So most people forget about the second derivative test. Although the exam sometimes asks you to show that you understand the second derivative test by saying, hence, one of those hence questions, or show that, if you've found the second derivative, hence show that certain point is a maximum, you're going to have to use the second derivative test to do that. So what we're going to do now is we're going to go through 4 different examples and use the second derivative test to find out if things are local minimums or local maximums. So to use the second derivative test, we're going to need to have our derivative, which is just 3x squared minus 6x. We're also going to need our second derivative, now to find a stationary point, our first derivative needs to be equal to 0. If we set that equal to 0, we can factor this. And we get x equals 0 and x equals 2. And now when we plug in those values into our second derivative, so if I plug in 0 into my second derivative, I'm going to get negative 6. And because it's negative, I know that my original function is concave down at that point. And when I look at 2, the second derivative at 2, 12 minus 6, I get positive 6. So I know that my original function is positive at that point. So we have two stationary points. At those two stationary points, we have one that's concave down, one that's concave up. So now we can find out what are our stationary points. And again, your stationary points are on your original graph. So when you go to list them, well, I know the x-coordinate is 0, but to find the y-coordinate, since it's on my original graph, I have to plug that back into my original equation. So when I plug in 0 into my original equation, I'm going to get negative 2. And based on the information in the second derivative test, because at 0 it's concave down, we know that this one is a local max. Our second point, when x is 2, and if we plug this back into our original equation, we're going to get 8 minus 12 is negative 4 minus 2, negative 6. And because our second derivative at 2 is concave up, we know that this is a local minimum. And if we wanted to, we could draw a quick sketch of this. We've got 0, negative 2. We've got 2, negative 6. We know that 0, negative 2 is a local maximum, and 2, negative 6 is a local minimum. So we have a basic idea that our graph looks like this. So we didn't have to do the first derivative test where we draw our number line, put 0 and 2, find out where our derivative is positive and negative. If we would have done that, what would we have found? If you plug in a number less than 0 into your first derivative, like negative 5, you get a negative number times a negative number, which is positive, which would have told us our graph is increasing. From left to right, sure enough, it's going up until we get to that point. Similarly, in here, you would have found this to be negative. Plug in one positive number times a negative number, and then afterwards found out it's increasing as well, so it would go back up, which our graph shows that as well. Just a little bit of review from the other day. If I made my second derivative equal to 0, can you see that you would get x equals 1? And at x equals 1, right there, on my graph that I drew, can you see that it's changing from being concave down to concave up? And if we wanted to plug in 1, we could actually figure out exactly where that point would be. Okay, that's a bunch of review stuff as well, but now let's just go to the next examples, and we're just going to focus on the second derivative test to find out where we have our stationary points. So I'll get you to start by finding the first and second derivative on your own. And then if you want to work ahead, you can, but I'll give you a little head start. All right. So there are both of our derivatives. We have something interesting happening this time. We've got 3 different possibilities for stationary points because we got 3 places where the first derivative is equal to 0. When we go to use our second derivative, it works well with 1 and negative 1 because we get positive and negative. So from that, you know that, oops, wrong. Screen is frozen. There we go. If we plug in 1, you'd get 1, negative 2. And because the second derivative at 1 is positive and that's concave up, we know that's a local minimum. I always like drawing these either positive or negative cyclops here because they really help me see right away whether it's a local minimum or a local maximum. So 1, negative 2 is going to be a local minimum. At negative 1, if I plug that in, I'm going to get negative 3 plus 5, negative 1 comma 2. That one's going to be a local maximum. What's going to happen at 0? When the second derivative is 0, that is going to be an inflection point. I don't know if I'm using the US spelling there or the British spelling. Does your textbook use an X? Can't remember what we... So the British spelling uses an X. Sometimes the US textbooks use C and T. So there we go. That's most likely going to be an inflection point. Now I said most likely because there are some possibilities where it could still have the second derivative equal to 0, but it's not an inflection point. But right now we're not going to worry about that because we've got our 2 stationary points. And if you were asked to graph this completely, we could tell more about that point if you did the first derivative test and found all your inflection points and did your diagrams for that. Okay. So again, find your first and second derivative. So once you've got your first derivative, got your product rule, so you keep on the same derivative of the second. And you might notice, oh, I could factor that. And if you factor that, you'd get e to the x times x plus 1. Now for your second derivative, you could either find it with either form. If I used the first form, can you see that I have the same derivative again? This x e to the x, when I do the derivative of that, I'm going to get that exact same thing again, plus the derivative of our second one here, it's going to be that again. If I used my factored form, well, I would have derivative that plus that. They're both the same. Because now if I factor an e to the x out of this one, I'm going to get x plus 1 plus 1, or x plus 2. And if I factor an e to the x out of this one, I'm going to get x plus 1 plus 1, x plus 2. So either way, often when you're doing the second derivative, it is helpful to do some simplification first, and then that helps you get the derivative. I think in this case, it looks like it's about equal, whether I simplified and factored that first derivative and then found my second derivative, or if I just started with what I had to begin with. Either way, we now have to figure out when is this equal to 0. Well, this part is easy, right? That's going to be x to the negative 1. What do we know about e to the x? And this is where I find it's helpful sometimes when solving to go back to what you know about the graph. The graph of e to the x, our exponential graph, looks like that with an asymptote here. Does it have any x-intercepts? No. So this one, this value here, e to the x, couple things. First of all, it's always positive, and it never equals 0. So our only stationary point is going to be at -1. And when we plug -1 into here, we get e to the -1. Is e to the -1 positive or negative? Positive, because it's equal to 1 over e. That's a positive number. I like that noise. Made it sound like I got the answer right. So now what do we know? We know that our point, when x is -1, and when we plug that back into our original equation, we get negative e to the -1. We know at that point we have a local minimum. All right, one more. So we could either do our first derivative with the quotient rule, or we could change this x squared plus 1 because it's on the bottom and bring it to the top by making it x squared plus 1 to the -1. And then we could use our power rule and chain rule. Either way, we get -2x over x squared plus 1 all squared. Now when we do our second derivative, the bottom stays the same, derivative of the top minus the top stays the same, derivative of the bottom, and the bottom has a chain rule. Sorry, it got a little small there. But the 2 would come out in front, x squared plus 1, and the derivative of the inside would be 2x. And then on the bottom, it gets x squared plus 1 to the 4. So now what I'm going to be doing here on my second derivative is I notice that there's an x squared plus 1 here, and there's an x squared plus 1 there. So I factored that out in front. The reason I'm going to do that is because then this is going to cancel out with one of these, and you'll have only cubed. Hopefully that makes simplifying that a little bit easier. So now when I look at the top, I'm going to have -2x squared minus 2 plus 8x squared all over x squared plus 1 cubed. And you probably don't have lots of room on your paper. Sorry about that. And we're left with 6x squared minus 2 over x squared plus 1 cubed. Now, the nice thing for our critical points, if we make our first derivative equal to 0, we can see that the only way a fraction is equal to 0 is if the numerator is equal to 0. So x would have to be 0. And the nice thing about 0 is it makes plugging into other equations easy. So when I plug in 0 into my second derivative, we're going to get -2 on the top and 1 on the bottom. So a lot of algebra for our result that wasn't that hard to plug in. So now we know that our point 0, comma, and I'll just scroll up to see my original equation, 0, comma 1 is a local max. Typical of an old exam question, it starts off by having a bunch of different parts, finding the derivative. That's not too bad. It gives us the graph. Find the x-coordinate of m. What do we know about m? We know that it's a local maximum. So we ask ourselves, how do I find local maximums? Well, I always find my local maximums with either my first derivative test or my second derivative test. But either way, I make my derivative equal to 0 and try to find the x values that work for that. Here, this factors nicely to x plus 5, x minus 1. So we know that our derivative is equal to 0. In other words, our tangent is horizontal because our slope would be 0 at negative 5 and 1. What's the x-coordinate of m then as a result? Is it negative 5 or is it 1? It's got to be the negative 5 because we're given a graph and m is the negative value. The x-coordinate of n then, well, what do we know about n? It's a point of inflection. So because it's a point of inflection, we're going to need to use our second derivative. And our second derivative is equal to 2x plus 4, and it's equal to 0 when x is equal to negative 2. Since that's the only place where the second derivative is equal to 0, that must be the x-coordinate of n. And finally, D here, we've got a line L. It's tangent to 3, 12, which looks like it's, off the graph here somewhere. And we want to find that equation. Well, how do we find equation of any line? We need two things to find the equation of a line. We need a point, and, which we already have. What else do we need? The slope. So if we're trying to find the slope, what finds us slopes in calculus? Our derivative. Our first derivative finds us our slope. So if we want to find our slope when x is 3, we can plug that in. We get 9 plus 12 minus 5. It's a big slope, 16. And then at this point, you can find your equation of line with whatever you're more comfortable with. If you're used to using y equals mx plus b, or if you're used to using the point slope formula, you can choose either one. In y equals mx plus b, you know your slope, you know a point, you know that when x is 3, y is 12, and then all you have to do is solve for b. And once you've solved for b, then you can write your equation. If you're used to using the point slope formula, you plug in your point. You know that y is 12 when x is 3. And you get the same equation either way.